Hi everyone, welcome to part 4 of lecture 10, and in this lecture we will discover the conditional distributions. So remember that we can condition a random variable x on an event e, and that e means we will given a piece of information, some extra information, and the e should be strictly positive. Okay, the probability of e should be strictly positive. So then we can talk about the conditional probability mass function or conditional probability density function. So if you are working with discrete random variables, you have to work with conditional PMF, or if you are working with the continuous random variables, you have to work with conditional PDF, the probability distribution function. So sorry, probability density function. So if x is discrete, we have the probability of x given e, so which is equal to the x will take some values, which is represented by the small x, and given that event e. So remember from the definition of the conditional probability, we can calculate this kind of probabilities as the probability of the intersection of the two events and divided by the conditioned event. Okay. So the same logic here, this probability can be calculated by the probability of x intersect e divided by probability of e. Okay, and also you can exercise if that is a legitimate PMF. Just simplify by checking the probability axioms. Similarly, if x is continuous, in this case, instead of PMF, we have to use the PMF, right? Instead of probability density function, we have to use the probability mass function. So in this case, we can define a non-negative function f x given e. So that is changed the PDF, the modified PDF that satisfies the probability of x in f. The f is a set of numbers, and the x takes the values from that set, and given e, that is a conditioned event, which will be equal to the integration of the modified PDF over the domain f, because the x can takes the values from that set of numbers. Okay, and this formulation is valid for every f. Okay, so this can be a little bit complicated when you look at this kind of the formulations. That can be a little bit complicated, but I will try to make it more concrete by giving you some examples. But first, it is important that these two formulations can be a little bit complicated when we think the e can be anything. But in the special case, if e as defined as equal to x is in a, so that's mean x will take some values from the a set of number, and we know that also e from that set of numbers. Okay, so in this case the things will be much more simpler. Like if x is discrete, so we will have that the probability of x, and we know that this x from e, or in other words, that piece of information given, like e in this case, the probability of x given that e, and e is defined as x in a, and the probability of x will be the probability of x is equal to small x, given that this capital X is in A. Okay, so if I want to explain this equality verbally, as I say, the x will take some values from A, and we will define the E as the x in A. That's mean the x will take some values from a set of numbers, and also we know that the given information, the given event, is also from the same set. So in this case, we can simply calculate that the probability of that conditional probability will be equal to probability of x is equal to x and x in A divided by the probability of x in A. So I will make these things more concrete a little bit later. And also we can rewrite this part. So what is this guy? What is the intersection of these two events? Which is simply the probability of x, right? Because let's say we have some sample space and we have some points here, okay? And let's say that given information is this region. So that's mean we know that x will takes the values from this region, and we call this region as event E, right? Or in this case, you can define it as E. So we know that the x will takes the values from this region, right? Let's say, which is the x. So what is the intersection of this event, okay, that is conditioned event, and x, which is simply the x, right? Which is the intersection. So that's why I can rewrite this part as the probability of x. And then I have the probability of x in A, which is actually this one, okay, in the denominator part. So if x in A, so if x takes the values from this region, I know that the conditional probability can be calculated as the probability of x divided by probability of x in A. Okay, otherwise, if x takes the values rather than this region, the probability will be 0, because that is the conditional probability. Okay, so the logic is the same. As I said, if the conditioned event and x takes from the same set of numbers, these things will be much more easier to calculate, because I know that in this case the x and that event, the intersection of that event, will be the x, and also I will just scale that term with the conditioned event. Okay, so this is how I can calculate the conditional probability. So let me give you a concrete example. Let's say we have a random variable x, which is a binomial with the parameters n is 10 and the p is 0.4. So that is the probability of success, and that is the number of trial. So that is like that the number of flipping a coin. So I will flip the coin 10 times, and that is the probability of getting the hat, okay, or probability of success. So if I graph that binomial random variable, I will come up with this kind of graph. That means if the probability of getting 0 hat, getting 1 hat, getting 2 hat, etc. And also I can get all of them hat, right? So all trials will be success, which is 10. And the y-axis will correspond to corresponding probabilities, okay? And the x-axis is just the number of trials. And this graph is for the unconditional situations. So I'm not given any kind of extra information. I'm not given a conditioned event, okay? So let's say now I'm given an extra information. So which is the given that x will be between 4 and 6. So x is the greater than or equal to 4 and less than or equal to 6. So that's mean x, I know that I'm given that x will take 4, 5, and 6. So let me ask you that one. In unconditional situation, what is the probability of x will be equal to 4? Probably, not probably, for sure, that is less than the probability of x is equal to 4 if I know the x values is 4 or 5 or 6, right? So that's mean I have to scale up the probability of x is equal to 4 in the case of unconditional situations if I given some extra information. And that scale will be based on the conditioned event. So what is the probability of x will take 4, 5, or 6, and that is the probability of the conditioned event, right? I can simply sum the corresponding probability, the height of these bars, okay? So like 0.25 plus 0.2 plus like 0.11, let's say. So that is the summation of these two individual probabilities will give us the probability of x can take 4 or 5 or 6, and that is the probability of conditioned event, okay? And that is some kind of number like 0.25 plus 0.20 plus 0.11. I say 11 because that is not exactly 0.1, and let's say that is a 0.11, okay? What was the formulation telling us, which is simply the probability of x divided by the probability of conditioned event. So for the x is equal to 4, what is the corresponding probability? What is the probability of x is equal to 4, which is 0.25, right? So that's mean I will scale up that probability by dividing this one to this one, right? So that will be approximately 0.25. So that's mean I will just increase the probability of the individual case under the given information. This conditioned event. Okay, that is the simple logic behind the conditional PMF or conditional PDF. So if the case is the continuous random variable, the logic is the same. Instead of, so in this case, we will use the integration, right? If x is continuous, now we had the probability of x in f. Okay, so x will take some f values or some values from f, given some piece of information that is defined as the event A. In this case, I have to integrate the conditional PDF, that is the modified PDF, over the domain of f, because the x will take the values from f, and that is valid for every f. But we also have, when the E is equal to x in A, so that's mean, again, the x and A will come from the same region, okay? So instead of thinking that points, now assume that we have a line, so because that's a continuous one, and let's say the x will take the values from this line, the line section, and also the condition event from this one. Okay, so x will take some values from this one, and the conditioned event is this one. In this case, the works will be much more simpler. Okay? So what I need to calculate the probability of x in f, given that x in A, which is equal to the intersection of these two events, okay, and divided by the probability of conditioned event, which is equal to probability of x in A. So I know how to calculate the intersection. I just need to evaluate the PDF of f of x over the domain A intersect f, okay? Instead of evaluating that integration for all possible values, I just need to evaluate that PDF for the given given section or given part, okay? So like if we think that as a line section, that should be the intersection of A and F. That is the valid limit of that integration. So we can conclude these equalities like if x in A, the probability can be calculated as the PDF of x divided by the probability of x in A. So the logic is same as the discrete case. Now, instead of doing this calculations here, so some kind of summation in this part, now we have to take the integration of the corresponding terms, okay? Otherwise, 0. So if x takes the values rather than this region, so the probability will be 0 because we are given some information that tell us the x is coming from this region, okay? If that is outside of that region, the probability will be 0. So so otherwise that will be 0. So if I want to calculate the conditional probability, conditional PDF of a random variable, and if that is a continuous one, in this case, I can use that formulation. So it is simply the PDF of x divided by the probability of conditioned event, okay? So to make it more concrete, assume that which is the unconditional, this line, this curve, like the unconditional PDF, okay? So the x is normally distributed random variables with the parameters mu is equal to 1 and the sigma square is equal to 1. So, so that is the unconditional one. But now, again, because I'm given some piece of information, that means I make my sample space smaller so that I have to scale up the unconditional probabilities. So the given information that x will be between 1.5 and 2, right? So that's mean if the x is outside of these regions here, so the probability will be 0 based on these formulations. If x takes the values within that region, so I have to scale up that probabilities, that corresponding probabilities, by using this formulation. So simply just I have to divide the PDF of x by the probability of conditioned event. So that is simply the scaling up the unconditional probability. So that will be scaled up to this point, and that makes sense, right? As I said, like let's say I have some events, right? Okay, so if I ask you, I will randomly select. I have randomly selected a point from this one. Let's say 1, 2, 3, 4, 5, and 6. Okay, I'm asking you, I have randomly selected a point from this region, okay? And guess what I selected? So what is the probability of your answer is true? Or you will correctly predict what I selected. Your chance is 1 over 6, right? But if I ask you, I have randomly selected a point from this region, and that is 1 or 2 or 3. So in this case, you will correctly predict it by 1 or 3, right? So that's mean by giving some extra information, I have scaled up your unconditional probability to 1 over 3. Okay? And same logic for the continuous case. Let's say we have a line and I can choose any piece of line segment from this line, okay? Let's say I have created some segments. That's 1, 2, 3, 4, 5. So if I told you again, I have randomly choose one segment from this line, okay, or any number. So your chance is less than for the same questions under the case of given some piece of information, right? Because if I don't give you some extra information, you have to evaluate all possible values within that line. But if I give you some piece of information, let's say I am asking you the number I have choose within this range. So now your probability, your chance will increase, right? Because I have make smaller uh, your sample space, your options, okay? So that's why the conditional events will scale up the unconditional events. So that is the main and basic logic behind the conditional PDF and the PMF. So the conditional expected value of x given an event E can be calculated using the conditional PMF or PDF. So if you want to calculate the expected value of x under the given E, if x is discrete, you can sum the x time corresponding conditional PMF, and fx continues. You can integrate x times the conditional PDF. Okay, so that's for the expected value of x given E. And same for the variance. If you want to calculate the variance of x given E, in this case, you can calculate the variance if the x is discrete, the summation of x minus expected value of x given A square. Okay, for that is for the discrete case. For the continuous case, the same logic. And sorry, here there is a corresponding the probability. So if you want to calculate the variance, it's simply the summation of x minus expected value of x given A squared times corresponding conditional PMF. And for the continuous case, which is x minus expected value of x given A squared times corresponding the conditional PDF. Okay, so you can use this formulations to calculate the expected value and the variance of x under given some piece of informations. Okay, you don't need to memorize these formulations. If you have any questions about these things in the quizzes or exams, you will be given these formulations, but just try to understand the logic. Similar to the unconditional version, we have the alternative formula for the conditional variance. So if you want to calculate the variance in another way, you can simply calculate the variance of x in given E for the x is discrete, the summation of x squared times corresponding probability, the conditional PMF actually, conditional probability, minus the expected value of x given A square. Okay, so for the continuous case, the variance will be the integration of x squared times the PDF of the corresponding conditional PDF minus the expected value of x given A square. That is exactly the same as the variance of x is given E is equal to the expected value of x squared given A minus the expected value of x given A squared. So remember that how we calculated the variance in the previous lectures, which is like expected value of x squared minus the expected value of x squared, right? So we have just added the condition event here, okay? Everything else is same. So the logic is same. We have just added the condition event, okay? So by thinking in this way, you can make all these things more concrete, and you can understand or you can comprehend the logic behind these formulations. So let me give you an example. And let's say we have a random variable x, which is exponential with the parameter lambda is equal to 0.2. How we can calculate the expected value of x given x is greater than 5, okay? And we will calculate this using the conditional density. And also can we do the same things without using the conditional density? So which is the exponential, right? So remember that the exponential distributions have the memoryless property. You can think that x as a lifetime of a machine or something. So we know that axes start from here, or the machine starts from here and come to the some points, let's say, which is 5, and it still continues. So that's mean we are asked, until that point, machine works properly, okay? And what is the expected value of x, which is, I mean, how we can, or how long that machines will work properly um, in the next or after 5, let's say, day, year, or something, okay? How we can calculate the expected value of the exponential distribution, which is 1 over lambda, right? Okay, without using any formulations, we can calculate like until this point. I can use this formulation, which is 1 over lambda, that's mean 5. So the expected value of x is 5, and that is in our hand. Now, regardless of what happened in the past, because the exponential distribution has the memoryless property, I can do the same thing for the next, okay, for the future. Again, for the 1 over lambda, this part is 5. So the expected value of x is 5 plus 5 is 10. That is a valid calculations if the distribution is the memoryless property. But now let's do that by using the math, by using the given formulations. So we have the probability of x is greater than 5 is simply the integration of the PDF of x over the domain 5 to infinity, right? Because x x is greater than 5. That's why we have to start. We have to start from 5, right? So that is, remember the PDF of the exponential distribution, which is the lambda times e to the minus lambda x. So which is 0.2 times e to the minus 0.2 x dx. That will give you the asked probability, but you don't need to calculate that one, because instead of calculating that one, you can simply calculate 1 minus CDF of x, right? Because remember that the CDF gives the probability of x is less than or equal to some values, in this case, which is 5, right? That means which is equal to uh, 1 minus the probability of x greater than 5, right? In other words, for that one, I can write the 1 minus probability of x is less than or equal to 5. And that is the CDF of x. What was the CDF of the exponential distribution, which is 1 minus e to the minus lambda x, right? So if I put this formulation here, I will end up with e to the minus 0.25, that is equal to e to the minus 1, right? So the probability of, or the conditional CDF will be, in this case, so what is the conditional CDF here? The x given x is greater than 5, okay? In this case, in this given information, what is the corresponding probability for any x? The CDF will give us that one, right? So, sorry, the PDF. What was the formulations? Look at this one. the PDF of x divided by the probability of x in A, right? The conditioned event. So what is the conditioned event here? X is greater than 5, right? What is the probability of conditioned event? What is the probability of x is greater than 5? We have just calculated, which is e to the minus 1. So denominator will be e to the minus 1. What is the PDF of x? We know that because that is an exponential exponential with the parameter lambda is 0.2, which is lambda times e to the minus lambda x. So 0.2 times e to the minus 0.2x. That is a valid conditional PDF for x is greater than 5 because we have made these calculations for that condition event, okay? And otherwise, that will be 0. So that means x is, if x is less than or equal to 5, the probability will be 0. Okay, so the question is the expected value of x under this situation. And x is greater than 5. So which is the integration of 5? Integration of the x of x times the corresponding conditional PDF. We just calculated it over the domain from 5 to infinity, right? Okay, now we can do some simple math to solve that. This one, okay, that integration. Let's define u as equal to 0.2x so that the du will be 0.2 dx, right? So that's mean, let's say this guy is equal to u, and this 2 guy is equal to du, and x is equal to u over 0.2, okay? So, okay, so, and we also have 1 over e, right? So this guy, there's u over 0.2, which is equal to 5u, and that 1 over e will be in the multiplication, so that will be 5ue, and that 5 and e is the constant, so that can go outside the integration, and we will end up with u times e e to the minus u du. So now let's look at the limits. If x is 5, the u will be 1, and if x is infinite, the u will be infinite. So that is the integration we need to solve. Okay, to solve this one, we can again do some modification, like let's say dv is equal to e to the minus u du, so that we will be equal to minus e to the minus u, right? So let's say, so that will be, if I use that one, the first things will be u times v, right? U times v. So what is the v? Which is minus e to the minus u, minus e to the minus u, and u. So we need to evaluate this from 1 to infinite, plus, sorry, minus the integration of v du, okay? So which is the du, and what is the v, which is minus e to the minus u. So 2 minus will be plus, the multiplication of 2 minus will be plus, so that will be the plus. If we evaluate these things, that will be the first term for the infinite, that will be 0 because this guy will decrease much faster than this one, so that will approach to 0. So that will be 0 minus. For the 1, that will be minus e minus e to the minus 1, right? If I put the 1 to the u, that will be minus e to the minus 1. For this one, the integration of this guy is minus e to the minus u from 1 to infinity. Again, that will be 0 for the infinite, and minus e minus 1. So we will have 5e times, again, 5e is coming from this one. This guy will be e to the minus 1 plus, that will be 0 minus e to the minus 1. Why 0? Because if I put that, if I put the infinite instead of u, that will be, that will approach to the 0, right? So that will be 0 minus e to the minus 1. Let's do that. The 5e e to the minus 1 and plus e to the minus 1, right? So that will be 5e times 2e. These two guys will cancel each other, and we will end up with 10. Okay, so the results didn't change. And this is how we can calculate the expected value of the conditional, expected value of a random variable under some condition, okay? Okay, so in the next part, we will continue to the conditional distributions. So far, we have discovered unconditional distributions, but now we will see how we can use the conditional distributions, okay? So I will see you in next part.